I don't know why my dad gave it to me.
Okay, so what I want to do is start by talking to you about what a graph of a polynomial function will look like. And I want to remind you that last time we talked about what a polynomial was, or not last time, but the time before. We talked about a polynomial could be a constant number like 4. We talked about it could be like 3x. We talked about it being like 4x squared or 4x plus 1. It was really any combination of numbers and variables added together, right? So today we're going to talk about what their graphs are going to look like. So I want to bring up a few points of some polynomial functions that you already know. Okay, I'm pretty sure that you already know, let's see if I can get this to right now, an example of a line, right? Everybody knows what a line looks like? It's a polynomial function. Can anybody think of any other graphs they already know?
A parabola?
A parabola. Okay, a parabola, does anybody remember what it is?
Is that the U-shape?
Yeah, it's like the U shape this way or the U shape this way, right? Right side up or upside down. Parabola. We already know that that's an example of a polynomial function. Okay, so think about the characteristics of the polynomial functions that you know for just a minute and tell me things that you might know about them. Tell me, maybe I should ask the question, do they have holes in them? No? Has anybody seen a graph before with a hole in it? Yeah, so sometimes you'll see something that looks like this on a graph. It will start like this, come with a hole in it like that. Have you seen a line before that probably looks like that? Okay, this would be a hole in a line. It's a non-example. It's not a polynomial function because it has a hole in it. So if we're going to list the characteristics of a polynomial function, we're going to say that it has no holes. Okay. We're also going to say that it's something called continuous. Does anybody know what it means to be continuous? Go ahead and tell me if you do.
It goes on forever and ever and never stops regardless of the situation.
Yeah. So the way I like to describe it to you guys while we're doing it in math class is if you're looking at a graph and you can put your finger on one end of it and you can trace it the whole time without having to pick your finger up to go somewhere else, then it's continuous. Okay? I want to show you an example of a non-continuous function so that you can see what I'm talking about. If we were looking at a graph, we've seen these kind of functions before that look like this. Does anybody remember what those are called? They're called step functions. Do you see how if I were to put my finger on one of the graphs and then come up, I would have to raise my finger off the paper. It's not continuous. Does that make sense to everybody? Okay, the other thing then, besides having no holes and it has to be continuous, the other thing that you need to know about it is that it can't have anything called a cusp. Have you guys ever heard that word before, cusp?
Yes.
It's spelled like this. Okay, a cusp is when you're looking at a graph and it has definite sharp points like here and here. Okay, those sharp points right here would be called cusps, and a polynomial function can't have those. Okay, so no sharp points. So again, if we're looking for a polynomial function, we're looking for a graph that has no holes, is continuous, and no cusps, which is another way to describe, sometimes we just say that it's smooth. Okay? So if it's smooth, it would be a polynomial function. To not be a polynomial function, it could have a cusp, it could have a hole, it could be not continuous. Are you following me on what the graph should look like? Okay, so we're going to go and we're going to start looking at some of the graphs here of some continuous functions. But before we do, we're going to review what function notation is, just like we did on the bell work, okay? So again, the f of x value right here, it really just stands for y. So every time you see f of x, you can think of it as your y value or your output value on a function. So right here, if you have f of x equals x squared minus 3x plus 5, what's the value of f of 3? How are you going to figure that out? put the 3 in, right? So it's going to be 3 squared minus 3 times 3 plus 5. And you're going to just simplify that according to order of operations. So 3 squared is 9. 3 times 3 would be 9. So 9 minus 9 plus 5. So what's your answer? It's 5. Okay, so what that said was if we put the number 3 in, we get the number 5 out. Do you guys agree with me on that? Okay, so I want you to look at this graph over here for just a minute. And I want you to decide if what we just figured out was actually on the graph. So we decided if we put the number 3 in, we got the number 5 out. So looking at the graph here, if you put the number 3 in, did we get the number 5 out? We did. It's that actual point right there on our graph. That if you put 3 in to your graph, what did we get out? We got out 5. Okay, so using just the graph then, answer the questions, what's f of 0? So this is saying that your x value is 0. So when you go and look at your graph, find where your x value is 0, which is right here. And then what's your y value going to be? It's 5. So your y value would be 5. And if we wanted to write that as an ordered pair, we could say when we put 0 in, we got 5 out. Okay. Then the same thing with f of 2. When you put 2 in on your graph, or when you go over there and you look at where 2 is at on your graph, it's up here, which would be your value of, right here, it would be at 3, right? So when you put 2 in, you got 3 out, or f of 2 equals 3. Both of those are appropriate ways to write the function. Okay? All right, so we're going to talk about something called end behavior for just a few minutes. And you're going to think I'm going on kind of lengthy, because I am. But end behavior is something that we use for the entire year. So I want you to really understand this, okay? Okay, if we look at the chart right here on the first box, we use this chart by telling whether or not our function has an even degree, an odd degree, whether or not its leading coefficient is positive or its leading coefficient is negative. So we would look at the degree, and there's some examples here for you, like this top one right here has a power of 4 on it. That's even, right? Power of 4 is even. So we know that the power of 4, the power of 6, the power of 8, the power of 2, all the even degrees have to have these end behaviors. If you're going, and this is the tricky part right here, so look at this right here, and let me read it to you, and let's write down exactly what that means. So it says my x's go towards negative infinity. So think about your graph for just a minute. If your x's are going to negative infinity, are you going left or right? Left, right? So really what this says is I'm going left. So if I'm going left, my y values are going up because I'm going to positive infinity. Does that make sense? What this language is telling you here? Then the one below it says your x's are going towards positive infinity. If your x's are going to positive infinity, that would be right. So you're going right. Then your y values or your graph is going this one up because it's positive infinity. Okay, are you guys following me on how to read this? This one says if you're going left, your y's go down. If you're going right, your y's go up. That's this one right here. So you can read it left and right and up and down. Okay? And I know this is confusing, so let's just try some. All right. We have an example right here. First of all, look at the power. Is it even or odd? It's, what's 4? Even or odd?
Even.
It's even, right? So we know we have an even power. And what's the leading coefficient, positive or negative?
Negative.
It's negative. So if I wanted to go back and look at that chart for just a minute, I'm going even and negative. So go back for just a minute and follow your chart. You're going even, which is this one. You're going negative, which is this one. And you kind of just match them up there like that. So do you see where you're going to get your answers from? Okay, let's go back and answer our question then. So we're even and negative. As we look at our x's approaching positive infinity, what are our y's doing? So our x's are going positive. Our y's are going down to negative infinity. So my answer there is negative infinity. Okay. And then you can tell that just by looking at the graph. As your x's go positive, your y's are going down. And here, as your x's approach negative infinity, so you're coming this way, which ways are our y's going? They're going to negative infinity. Okay, that's really what end behavior is all about, is it tells you which direction the end of your graph is going. And you're wondering why that would be important. It is in the next few weeks as we're graphing functions. It makes it really easy to graph a function by knowing these rules about it. Okay? All right, so this next one, again, the graph is there, so it makes it really easy to see. But you would look at the leading coefficient and the degree. This is going to be odd, which tells me that it's going to be following the same patterns that lines follow. Okay? This is odd and it's positive, which means it's going to follow the same end behavior as that line that had a positive slope. So read this one though, because this time I asked you in the opposite way. Did you see that we're still looking for our y values, but it said it backwards? It asked us over here to look at our x values. So as our x values are going to infinity, what are our y values doing? They're going actually up, right? So they're going to positive infinity. And then as my x values are going left, this one's left. That one was right. As my x values are going left, what's my graph doing? Going to negative infinity. Okay, this is called end behavior. Kaylin?
So we do that, we use the farthest to the right, because in that one it's going down to before it goes up. So we use the line farthest to the right.
Come and tell me exactly what you mean.
Like that one, it goes up and then down and then up. So the first one, the f of x.
Yeah, you're going straight to the end of the graph, where you think the end is, or in this case, where it's continually going in a certain direction. This part is going to be important in just a minute when we talk about some of the other stuff, this in-between part here. But for now, we look at the very ends of the graph and which direction they're going. Okay, thanks for that question. Okay, other questions on that? Okay. So same thing then on this one. Again, we're still just practicing end behavior. So I like to really just try to memorize what I know it's going to look like. So I know this is a power of 5. So I know it's either going to look like this as a line or like this as a line, right? There's only 2 ways that our end behaviors happen. So I like to think about it as a line that has positive slope or a line that has negative slope. So it could be this one if it was positive. It would be this one if it has negative. The power of 5 gives it curves in between, but it follows the same end behavior no matter what, okay? So when I look at this, I see that it had an odd slope, which told me it would follow the line's end behavior, and it told me it was negative, so I know it has to look like that. Are you guys following me on that? So then I can use my chart if you wanted to, or you can just say, I know what a line's supposed to look like, so I know what the end behavior is going to do. So this says as your x's go to the right, do you guys agree with me that positive infinity be right? So as your x's go to the right, what do your y's do? Well, as my x's go to the right, what are my y's going to do over here? They're going to go up to infinity. You could totally grab it off the chart to do that, or you can just think about what a line would do. Okay? Then as your x's go left, what would your y's do? Well, as your x's go left, your y's would go down to negative infinity. But again, if you wanted to do it off of your chart, you would grab the leading coefficient, which in this case was a -1, and whether or not it had an even or odd power, and it had an odd power, and you could just go look at your chart to get your answers. Okay? Next one. Somebody talk me through it. What do you think on number 3?
Leading coefficient is 1/4.
Okay, the leading coefficient is 1/4. That's truth. What's the degree, even or odd?
Even.
It's even. So go follow your chart. Find it when your leading coefficient is positive. Find it when your degree is even. And tell me what's going to happen on there. So even tells me, first of all, they're both going up like a parabola, or they're both going down like a parabola. Those are my only choices, right? Okay, because it's even, I know that. Because it's positive, it's got to be like the smiley faces and behavior. Okay? So as my values are going to the right, my x values are going to the right, what are my y values doing?
Going up.
They're going to infinity. As my x values are going to negative infinity, what are my y values doing? They are also going up. But it's really just reading that chart until you understand how to do it without the chart. Okay? All right. Couple more problems here on something different. This time we're going to talk about relative minimum and maximum. Does anybody know what a minimum and a maximum are?
Yes.
What's a maximum?
Highest number.
The highest point. You would think about that. So let's think about it for a minute. If we're talking about the highest point of something, isn't it usually at the top of something that went up and then down? Like it has a change in direction. True? Yeah. The same thing is true in mathematics. If you're looking for the maximum, you have to find the highest point where something went up and then came down. Okay? So when we're looking at this graph right here, it looks like it's going to go to infinity. Do you guys agree with me on that? But does it ever come back down from up there?
No.
No. So that can't be a maximum, because at the maximum you have to have a turning point. Okay? So as far as maximums go, I have a maximum right there, because it's either the top of the mountain or the bottom of the valley. Does that make sense? Okay, I have a top of the mountain right there for my maximum. What ordered pair would that be?
0 and 1 0.
1 0, that's correct. So my maximum is at 1 0. So minimum then at the bottom of a valley, because I have a change in direction, would be right here. What ordered pair does my minimum get represented by?
3 -8.
3 -8. Are there questions on how I did that? Yeah,
Question about this, sorry to interrupt again, but can I go to the office?
sure. Okay, number 4 over here. You're going to find the maximums and you're going to find the minimums.
Paper for me?
Okay, I can't do that right now, but you can come back after school.
Okay.
Okay. Do you remember when I said I was going to try and teach from this so it could do my recording at the same time? Well, I just messed it up somehow. All right, were we right here? We were right here on number 4. All right, if we're looking at number 4 right here, we're going to find the maximums and we're going to find the minimums of this. So maximums are, again, where we have a high point and a change of direction. So here and here. This time we have 2 maximums. What are their values going to be at? 1 0 and 3 0. Okay, so 2 ordered pairs for maximums. And then my minimums, I think you guys have